hello viewers, welcome back to the course on scientific computing using MATLAB. So, today we will go for the lecture number 32 and we continue from the previous lecture, that is Greshagorian theorem. So, in the previous lecture we have discussed about the Greshagorian theorem, and based on that one we have found that if I have a matrix n cross n matrix, then the maximum eigenvalue of this matrix, I am taking the modulus. So, that will be always less than equal to the maximum of a I j I from 1 to n and then j. So, I am taking the rows. So, in this case I am taking the sum of the magnitudes of the elements in the row and then I am taking the maximum over the all rows. So, that is, I think we should change this one to j, because and then this will be I, because this will be equal to, first I will take this one. So, this is summation a I 1 plus a I 2 up to summation a I n. So, modulus a I n. So, this is the ith row and then I take the maximum over the j. So, it will move from all the rows and then I will take the maximum. So, this is, so now from here you can see from here that now the question is, since matrix A and its transpose have same set of eigenvalues, so that we already know. So, from here I can write that the lambda max is also less than the largest column sum in modulus. So, I can also write the column sum. Okay. So, from here I can write that this max will be always less than summation. So, this is, so I can write max of j and summation a I j modulus I from 1 to n. So, that is the I am taking from here. So, this is, you can write from here that this is maximum of j and this will be a 1 j, a 2 j and last a n j. So, that is the 1 j, 2 j, that is the column vector we are taking and then we finding the maximum of all these. So, that is the largest column. And if we know from here, from the norms, matrix norm, so from the concept of matrix norm, we know that this sum, the largest row sum, this sum is equal to one. So, it is equal to infinity. So, that is basically infinity norm, and this is the maximum column sum and this can be written as 1. So, from here I can say that for any matrix I will get A max is less than and also less than 1. So, this is we have done from the Greshagorian theorem. Now, we want to do a corollary. So, let us so this is the application of the Greshagorian theorem. So, now from here that we know that from Gresham theorem, we know that we have written like this one: a I1 x 1 r over x L r. If you remember, a I L plus a I n x n r over x L r, and that can be written as lambda r over x r, this x r over x L r. So, this is, we have from the previous lecture we have seen that we can write this one as here. Now, in this case, so this is true for all rows. Now, from here what do we do? We choose the row with largest component. So, that is x L r. So, we just take the row that corresponds to the x L r, like in the, suppose for example, I have this vector 1 minus 2 3. So, in this case I am choosing the third row, because third row has the largest element. So, I am choosing that row which has the largest element, that is x L r. So, from here I can write that equation number, I can write 1. So, equation 1 can be written as, so I is the L. So, it will be L 1 x 1 r over x L r plus a L L up to a L n x n r over x L r is equal to lambda r, and that is, it will be only x L r divided by x L r. So, that will be 1. So, from here I will get this equation. So, that equation I just take as a 2. Now, I take the modulus value. So, I just take the modulus of this. Now, from 2 we can write that modulus of r is less than equal to a L 1 a L 2, or maybe I can take from here. So, before taking the modulus value, I just take, so just taking before the modulus value, I will take this component on the right hand side. So, take a L L on the right hand side. So, I will take this. So, I will get a. So, I can write from here, I can write that this part I can write minus a L L can be written as a L 1 x 1 r over x L r, and now this has gone. So, it will go up to plus a L L minus 1 x L minus 1 r over x L r plus a L L plus 1 x L plus 1 r over x L r, and in the end we will get a L n x n r over x L r. So, this I will get. Now, after doing this one, and then I take the modulus value, and from here I will take this modulus value, then this modulus value will be written as, so from here I can write lambda r minus x L L can be written as less than equal to this quantity a L 1, and this part I know that this is less than 1. So, I can ignore this one. So, from here I can write a L 2 a L L minus 1 plus a L L plus 1 a L N. So, from here I will get this value. So, now you can see from here that this is again the sum of the modulus of the lth row except that ALL. So, that is equal to the sum. So, this can be written as, now from here I can write that the lambda r minus ALL modulus value is less than equal to summation ALI, that is I from 1 to n and I is not equal to L. So, accept this value. So, this can be written from here, this value, and this is true for all eigenvalues, because I have chosen that only that row which has the largest value. So, similarly we can choose for the other eigenvalues and then we will find out this. So, this is true for all eigenvalues. So, now from here we will get another theorem, that is called the Brewer's theorem. So, Brewer's theorem says that if PL, that is equal to the sum of moduli of elements along the lth row excluding the diagonal element, that is ALL of matrix A, then every eigenvalue of A, that matrix A, that is n cross n matrix, will lie inside or on the boundary of at least one of the circle or disk, I can say lambda minus ALL less than equal to this one. So, now this is whatever we have done from here. So, I will just call it the equation number 1, 2 and this is 3. So, proof or statement is this one. So, as from equation 3 we can say that any lambda r minus ALL, that is always less than equal to summation ALI, I is from 1 to n and I is not equal to L. So, this is from the equation. So, I call it 4. Now, this is true for all eigenvalues, because I have taken a one eigenvalue, that is the rth eigenvalue, and that rth eigenvalue satisfies this relation. So, I will choose another eigenvalue, I will get the another relation, I choose another eigenvalue, then I get the another relation. So, this is true for all eigenvalues from here. So, using this one we can find the bounds for all the eigenvalues of a given matrix, and using this matrix we can give the estimation of alpha, that where the alpha is lying. So, let us do one example, that what is the meaning of this one. So, for example, let us take the same matrix what we have taken. So, this is my matrix A. So, 0, 11, minus 5, minus 2, 17, minus 7, minus 4, 26 minus 10. So, the question is find all Greshigorian circles. Or bounds for eigenvalues. So, now from here if you see, so I choose the diagonal elements. So, this is my diagonal elements, this and this. So, from here I can write that for the first circle I can write lambda minus 0 modulus value. So, this one is 11 plus minus 5 modulus. So, that is 16. So, that is from row 1. Now, from the second row I will get lambda minus 17 less than equal to minus 2 plus minus 7. So, that is equal to 9. So, this is from the second row, and from the third row I will get lambda plus 10 less than equal to minus 4 plus 26, and that is 30. Now, from here I can see that from here I will get the bounds. So, this will give me, it gives the lambda is less than equal to 16. Now, what I do is that I try to plot in the complex plane. So, I am plotting this one in the complex plane. So, this is the real part and this is the imaginary part. Now, I take the eigenvalue. First is that the lambda is less than equal to 16. So, I take a circle with the radius 16. So, it is a very big circle we have to draw. So, let us take, suppose this is my this one. So, that circle I have taken, and with the center is 0 in this case. So, this is my, so lambda is less than equal to 16. So, that becomes the disk. So, this is the part given disk we have to take. Now, from the second one is that lambda minus 17 is less than 9. So, this is going up to 16. So, this is 16. Now, I have to choose 17. So, suppose this is 17. So, I will take this as a center now, and I will take a circle of radius 9. So, let us take a circle of radius 9. So, 17 and it will go up to 9. So, it is 26. So, suppose I take this as a, this place I choose as a 26, and 17 minus 9 is a 8. So, suppose this is my 8. So, from here I will find a circle, write a circle, drawing a circle with the center this point. So, this is my circle with lambda minus 17 less than equal to 9. So, now it is less than equal to, so it becomes a disk. So, this is my another disk, and from the third one I choose. So, I choose the lambda plus 10. So, it means the lambda minus 10. So, it is 16, it is also going up to 16. So, suppose it is somewhere minus 10, and then I have to choose a radius of 30. So, 30 means I have to go up to 40, and minus 10 plus 30 is 20. So, suppose this is my 20. So, I have to choose a very big circle like this one, and this is my another disk. So, from here it says that from here that all all eigenvalues of matrix A will lie in the union of this circle, or all the eigenvalues of the matrix A will lie in any of the circle, or I can take the union. So, from here we can take that I can find this all the eigenvalues of the matrix A into the lambda 16. So, this is the first disk union lambda minus 17 less than equal to 9 union lambda plus 10 less than equal to 30. So, from here I will get this is the bounds for all the eigenvalues of the matrix, given matrix. Now, from here I can draw one conclusion is that, so from here I can draw one conclusion that if we have isolated disk or circle, then exactly one eigenvalue lies there, because we have seen from here that in this case this was the first disk that is also intersecting with the second disk, and I have taken the third disk that is also intersecting with all these two. So, this is completely inside this one and this is also intersecting. So, in this case there is no isolated disk. So, that is why we say that all the eigenvalue will lie in the union of this one. But what will happen if I have this type of disk? Suppose I get one disk like this one, another disk I will get like this one, and another disk I am getting like this one. So, in this case and suppose I have a 3 by 3 matrix. So, in the 3 by 3 matrix I will get 3 disk. So, one disk will be there. So, in that case the one eigenvalue will lie here definitely, and the two eigenvalue will lie in the union of this and this. So, that is the meaning of isolate value. So, one eigenvalue lies here and two eigenvalues lie here. So, that is the bounds we can find. So, let us take the one more example. I have matrix A. So, 4 1 0 1 2 1 and 0 1 5. So, this I have chosen. Then the question is estimate the eigenvalues of the matrix using Gregorian's bound. So, now we have this matrix. So, let us start doing this one. So, now in this case I know that from the Gregorian theorem we know that I will apply this formula, that the lambda is less than equal to 1, or I will get the lambda is less than equal to infinity norm. So, 1 norm is the maximum column and infinity norm is the maximum row. So, first is this one. So, case 1. So, in this I will find out all the bounds whatever is possible there. So, let us take this one. So, this is the maximum largest column sum and this is equal to the largest row sum. So, from here I can say that lambda, so I choose the largest column sum. So, this is the, I want to find the maximum of first column sum. So, that is 4 plus 1 5, 2 plus 1 3 plus 1 4 and this 6. So, that is equal to 6. Now, from here I will get, now from here I will get lambda is maximum over all row sum. So, that is 4 plus 1 5 and 2 1 3 4 and 6. Now, from here I will also get lambda is less than equal to 6. So, from here I will get my magnitude of lambda is less than equal to 6. So, this is the first bound I will get, case 1. Now, case 2, I will apply the Gaussian. So, in that case lambda minus 4 is less than equal to 1, lambda minus 2 is less than equal to 2, and lambda minus 5 is less than equal to 1. So, that is the Gaussian disk we are getting for this matrix. Now, from here if you see this one, so this is the case number 2 and I will take case 3. Since A and A transpose have same set of eigenvalues. So, what do we do in this case? Instead of I am finding the rows, I can take the column. So, in that case I will get my matrix. So, that is the matrix I will getting. So, I will get the matrix A transpose. So, this A transpose will be 4 1 0, 1 2 1, 0 1 5. Now, I can apply the Gaussian theorem here. So, from here I can write lambda minus 4 is less than equal to 1, lambda minus 2 is less than equal to 2 and lambda minus 5 is less than equal to 1. So, in this case if you see I am getting the same value, because for this 1 2, oh, this is a symmetric matrix. So, no problem. So, I can say that since A is symmetric, which implies that A is equal to A transpose. So, I get the same bounds. So, now from here I can say that from, so this is a, I can call it 1 and then 2 and then 3. So, 2 and 3 are same. So, from 1 I will get lambda is less than equal to 6, that gives me that the lambda is lying from minus 6 to 6. So, that is the one of the bound. From the second bound I will get from equation number 2. So, lambda minus 4 is less than equal to 1, that implies that lambda minus 4 is lying from minus 1 to 1 and that gives me lambda is less than equal to, I am adding 4 here. So, it will go 4 minus 1, it will be 3 and this is 5. So, that is the corresponding range of lambda. Lambda is equal to minus 2 less than equal to 2. So, that gives me lambda minus 2 minus 2 plus 2, and if I add, so it will be lambda from 0 up to 4. So, that is the another bounds, and the third bound is lambda minus 5 is less than equal to 1, that implies that lambda minus 5 is minus and 1. So, that implies that the lambda will lie from adding 5 here. So, it will be 4 and it will be 6. So, based on this one, so these bounds we have calculated independently, these bounds we are calculated independently. So, if I want to find that the minimum bound, so for, or I can say the stick bound, I will take the intersection. So, intersection gives me that my lambda is moving from minus 6 to 6 in this case, but it is moving from 3 to 5, 0 to 4 and 4 to 6. So, if I take the intersection of all these, I will get my lambda will lie minus 6, 3, 0, 4. So, let us take this one. This is suppose I take go 6, it is go minus 6, here I am going 3, so 5, and the lambda is moving from 0 to 4, right, and this is 4 to 6. So, if I get from here, widely I can say that my intersection is here 4. So, if I take 4 and then from here I get 6. So, I get this intersection point from 0 to 4, 4 to 6 and 3 to 6, but I suppose I want to take the left bound. So, left bound is minus 6, 3, 0, 4. So, if I take the intersection in this case and then from right hand side, so no, from here I will get this 0 and from right hand side I will get 6. So, that is the maximum all the bounds will get. So, you will see from here that from here I can say that all the eigenvalues will lie within this range 0 to 6. So, that we all about the eigenvalues. So, we stop here. So, today we have discussed the application of the Cauchy-Green theorem, and then we have discussed another theorem, that is the Brewer's, that is also the application of the Cauchy-Green theorem, and then we have discussed 2 example based on this one. So, in the next lecture we will continue from this one. So, I hope you enjoyed this lecture. Thanks for watching. Thanks very much.